Hello, and this session today is going to be about amides and polymers. It covers quite a little bit of ground, so the title may seem a little bit misleading at first, but let's start off with where we want to start off. So, like I say, amides and polymers. Start off with a bit of a reminder. We're going to look at carboxylic acids. Now, a carboxylic acid group has got your alkyl or aryl chain. It's got a C, double bond O, and an OH. It's an acid because this H can leave as an H+, leaving behind this group here with an RCOO-. Now, if you replace the hydrogen on this carboxylic acid, you end up with an amide. And an amide, therefore, looks like this. The alkyl or aryl group now that is an amide. Excuse me. That is an amide. So we'd have to talk about naming them first of all. So the naming would go, let's say this was a CH3 to start off with, and then a CONH2 with the H's around here. Now that would be ethanamide. Okay, so you're just going by the length of the carbon chain and taking E off and sticking amide at the end. The formation is not very important in your specification. You can look it up. They are formed from acyl chlorides plus ammonia. But like I say, in your specification, that's not terribly important. What is important is that you've got, in this case, an alkyl chain with an NH2 and a C double bond O. So it's got both a carbonyl group and an amine group on it. Excuse me. Now, in and of themselves, amides don't come into the specification very much. However, where they do come in is this thing called the amide link. Those people doing biology will have come across this as well, and we do this in more like the biology, sort of the biochemical section of the course. But let's have a little look at the amide linkage. So an amide linkage looks like this. We've got our carbon with our double bond to the oxygen, and then we've got an N linked to a hydrogen, and then that would be linked off to some other part of a chain. So that is the amide linkage. Now that is in various polymers, both biological and non-biological, and we're going to have a little look at how you actually form them. Now, you're used to the idea of polymers being formed by something which has a double bond. So, the simplest polymer is polyethene. So you start off with ethene, and if you have a second one of these molecules like this, you know already that this part of the double bond breaks. One electron this way, one electron this way, the same that way, and the same that way. So we end up with and this is just two of the ethene groups joined together. So you end up with this great big long chain of carbons with hydrogens on either side of it. The actual repeating unit here is a little difficult to spot, because you could say it is two of them like that, because that's what it is. But also, it's actually the same as having one of them just repeated all the way along. To do something which is a little bit more obvious to spot the repeating unit, the thing which carries on repeating throughout the polymer chain. If you did something like polypropene. Now, polypropene is formed from two of these. I'm not going to draw the second one, but it's the same idea. The one electron goes this way, one electron goes this way, and you end up with a carbon chain, a carbon backbone if you like, but every second carbon has a methyl group on it. Now I've drawn both of mine upwards, but they could equally well be both downwards or one up, one down. That's just the nature of the chain. Now, the question is, what is the repeating unit? What is the thing which repeats throughout the chain? And in this case, it's this, isn't it? You can see that it's two carbons, one with two hydrogens on it, one with a CH3 on it. Now, you have done this back at Key Stage 4 in your GCSE, and you were taught to write it basically like this. N times this. Lots and lots and lots of these all joined together. So this, anything that you would write in the brackets and put an N after it, is the repeating unit. It's quite hard to see in this one because you could say it's two carbons, you could even just say it's the one. But in this one, it's quite obvious that the thing that repeats along the chain is that. So that's just a little bit of review on polymers. Let's have a look at the specific polymers that we want to look at today. And we want to look at, well, I'd like to look at two. One of them would be polyamides and the other one would be polyesters. Now, we've already seen on this one here that the repeating unit is this group here. The linkage, is this. Not necessarily the repeating unit, but that is the thing that links the chains together. But how do we get that? Well, we need something that you can join to both ends, like you can with this. The reason why these alkenes polymerize so easily is because it's got the double bond, so you can join to both ends of the molecule. Well, we can join to both ends of the molecule if we have a dicarboxylic acid, for example. Let's think of the simplest dicarboxylic acid we can think of, and that is something like this. That would be ethane dicarboxylic acid. Okay, so we've got two carbons and two carboxylic acid groups on there. Now, this will react with, again, something which has on it two amine groups. That would be called maybe ethylene diamine. Okay, so we've got a diamine and a dicarboxylic acid. Now, what then happens is this group here reacts with this group here, removing water. So this OH and one of these two H's here are removed, and that is the step, like I said, that's like removing water. H2O. So it's called a condensation polymer. I'll write that down. It's a condensation polymer. Now, condensation is obviously when water is removed from the air, usually in forms of little droplets on glass, panes, windows, whatever. So in this case, it means the removal of water from the molecules to make the polymer. Strictly speaking, a condensation polymer actually means the removal of a small molecule. There will be other examples where you may have the removal of another small molecule, like, for example, HCl. However, I think in all the ones that you're going to see at A level, they're always going to be removing water. So let's have a look at what happens here. I'm going to leave this end and this end as they are. So this, if this removes this OH and one of these two H's, this carbon will be attached directly to that nitrogen there, which will still have an H on it. And you will end up with still these two carbons and your ammonia group at this end. I'm going to draw the hydrogen slightly differently this time. and still with your hydrogens in the middle. And then on this side, you're still going to have the carboxylic acid group. So you can see that there is the amide link in the centre there. Now, if you think about it, if there is another dicarboxylic acid at this side, which would be something like this, another ethane dicarboxylic acid, this H and this OH can join to this. And if there was another amine, let's say like this, I haven't got space to draw the full molecule. If there's another diamine at this side, you can see that this also will form a condensation polymer, and you will end up with a great big long chain, which, let me see if I can draw something similar to it. I won't bother with the end. So this end will have a nitrogen on it. We'll have 2 carbons, both with hydrogens on. This nitrogen here, attached to this carbon here. This is our amide link. Then we've got the two carbons from the dicarboxylic acid to another nitrogen. That'd be this one. 2 carbons, both with hydrogens on them again. Back now to this amide linkage. And back again to the dicarboxylic acid, which will again go off to form another amide linkage to the amide, and the whole thing will just carry on and on and on. The question you would be asked for this is, you could be asked to look at these two and say, what would be the repeating unit? Well, the repeating unit must start from one end of a molecule, go through that molecule, go through the other molecule, and then finish before you get to the next full molecule. So the repeating unit in this case is obviously going to be these 2 carbons and these 2 carbons, 1 full amide linkage in the middle, and then a nitrogen on one end and a carbon on the other. So the repeat unit for this polymer will be this. That is the repeating unit. That's the thing that repeats all the way along. It would be a mistake to put this nitrogen in, because that nitrogen is part of the next repeating unit. Each repeating unit must have 2 nitrogens in, 1 amide link, and finish at the other end of the amide link, so as if this could join to that. So that is our repeating unit, and that would then be a polyamide. Polyamide. The other type of condensation polymer which you will come across is a polyester. You've obviously probably all heard of polyesters. And a polyester is formed only very slightly differently. Now, a polyester, you still have your dicarboxylic acid, and I'll keep it simple again. But this time, instead of reacting with an amine, this time it reacts with a diol, something with 2 alcohol groups on it. This, of course, would be ethane 1,2-diol. So again, we will have exactly the same idea, only this time we will remove that water, so we will end up with, I'll just draw 1 repeating unit, sorry. So we'll start off with this oxygen here. Sorry, no, apologies. That carbon there. To this oxygen, 2 carbons with their associated hydrogens, and then that will have this oxygen here, which will go off and join to the next molecule. So that is our polyester repeating unit. It is still a condensation polymer because we've removed water, and that is the repeating unit, just as we did previously. Very, very similar to the polyamide. Now, one of the things that you can be asked is what are the advantages of polyesters and polyamides as compared to polythenes, polyethylene, that sort of thing. So when you polymerize something with a double bond in it, an addition polymer, this time because you're just adding them together, the only bonds you're forming are carbon to carbon. So you've got carbon to carbon bonds and carbon to hydrogen bonds. This thing is non-polar. There's no delta pluses and no delta minuses. So it's very difficult for these things to be attacked by anything, which is why they take so very long to decompose. On the other hand, in our condensation polymers, you can see quite easily that there are plenty of delta pluses and delta minuses here. You've got an NH bond there. Your nitrogen is going to be delta minus, your hydrogen is going to be delta plus. And you've got a CO bond there. The carbon is going to be delta plus, and the oxygen, is going to be delta minus. So because these are polar, these molecules have polar bonds in them, then they can be attacked by things such as water. This is your biodegradable polymer. This is the sort of thing that you get for the food bags that you can put your vegetable waste in so that they can go into the vegetable waste bin, so they can go into landfill and they will decompose. So that is a summary of what we need to know. I know I've titled this Amides. I titled this Amides, but there is polymers in there, and we did obviously start off with carboxylic acids. But we start off with our carboxylic acid. We've talked about the structure and nomenclature of amides and the fact that really you can go away and look up how you form an amide, but it's not that important. Useful background reading, let me say. The general idea about polymerization is there for the addition polymers, for the when you make things like polyethylene, whatever, polypropylene, and the concept of the repeating unit, which is something that you will have had from GCSE. We've got condensation polymerization, where we remove water in this case, and the idea that it is more difficult to find the repeating unit here, but the general rule of thumb is knock a hydrogen off each side, stick the two things together, and make sure you only have one of each of these two things in there. So that works for a polyamide and a polyester. And remember, like I say, there's the idea about the repeating unit. It's very similar for here and for here. And remember that these two, because they have polar bonds in them, they are now biodegradable, and that's what we use them for. Thank you very much for watching.